Hello everyone, my name is Sayed Mohsen Vazirizadeh and I would like to present our work Learning Incident Prediction Models over Large Geographical Areas for Emergency Response at the SmartCom 2021. Emergency Response Management (ERM) includes multiple parts. The focus of this research is this colorful part, in particular, Incident Prediction Model. The goal of this project is to help Tennessee Department of Transportation (TDOT) to keep highways safe. On this map, you can see the spatial-temporal distribution of incidents on interstate and highways of the state Tennessee. When an incident happens, TDOT wants to be on the scene as fast as possible. If it's a life-threatening situation, minutes or even seconds matter. Furthermore, they want to reduce the chance of a secondary accident due to the congestion by the first accident. And moreover, congestions cause indirect costs for the state by wasting time and resources. Proactive ERM has multiple components. First, we should collect data from the environment. We can use that data to detect the location and time of incidents even before receiving a formal report. For example, crowdsourced platforms such as Waze can be used to detect the time and location of incidents even before receiving a 911 call. Arguably, prediction is the most important component of this pipeline, which is a focus of this research. And strategic allocation and optimized dispatching can reduce the response time. The goal of the prediction component is to design a function, f, to predict the feature of incidents, such as interarrival time, frequency of incidents, or intensity, which we call it y here, using the information that we collect from the environment, such as precipitation, temperature, or traffic congestion, by adjusting the parameters of the model. Let's discuss some of the most important challenges in incident prediction. First, we have to collect data from the environment. However, most of the time, we don't have access to macro-level data. For example, the age of the driver and the type of the car are very important factors in incident prediction. However, we usually don't have access to that. Then we have to collect as much as macro-level data that we can. For example, traffic congestion, temperature, or features regarding the highway such as the number of the lanes and the length of the segment. Since these data sets are coming from various resources, integrating them is not a trivial task. While achieving a very high resolution prediction is virtually impossible, reducing the resolution may cause aggregation bias and unobserved heterogeneity. For emergency response management purposes, the incident prediction should be in a high spatial-temporal resolution. Although frequency of road accidents is high, when viewed from the perspective of total time and space, incidents are actually rare events. For example, on the figure on the right, you can see roadway segments on the y-axis and 4-hour time windows on the x-axis. The white cells are showing the presence of an incident. As you can see, most of this figure is black, which is showing 99.8% of the time there is no incident. Furthermore, since incidents are being influenced by various factors, they are inherently irregular events, which makes the prediction very challenging. This table summarizes the data sets and features we created or collected from various resources. We use historical incident events. We use visibility, wind, precipitation, and temperature for weather. We use traffic flow information. And we use static features for the roadways, such as number of the lanes, length, and inverse stretch factor representing the curvature of the roadway segment. We also consider a feature for time of the day and if that day was a weekend or not. After collecting and combining the features I explained in the previous slide, we use clustering techniques to put the similar segments together and train a prediction model for them. In order to reduce the sparsity level of the problem, we use synthetic resampling techniques. Then we use machine learning techniques, including logistic regression, neural networks, tree models, and zero-inflated Python models to predict the likelihood of incident occurrence over time and space. For the training, we are using the rolling window approach. For example, for predicting the incident occurrence for the month February in 2019, we are using the data before it. The test is shown in yellow and the training data set is shown in red here. For the next month, we will add February to our training data set to predict the incident occurrence for the March 2019. And we do this process for a whole year. By doing so, we will have 12 different data sets that we can use them to compare and contrast different models. This table is summarizing different models that we used in this work. Logistic regression, neural networks, tree models, or random forest, and zero-inflated Poisson model. The second column is showing our clustering approach, which can be no clustering or clustering using k-means. Then we have our synthetic resampling strategy, which can be no resampling, random undersampling, and random oversampling. And the last column is summarizing different techniques that are used for each model. The first row is showing the naive model, which is our baseline. This model works based on the average of historical incident. This table compares different models using different performance metrics. It's also color-coded. The green values are better values. For example, we can see using the accuracy performance metrics, naive model is relatively better than the other models. While naive model is good based on accuracy, Pearson correlation, and a Spearman correlation, random forest and neural networks model performs better based on recall and F1 score. However, the question is, which one of these metrics it should be used to decide which model is the best? In order to answer this question, we run a simulation. We distribute a limited number of resources, ambulances or response trucks, on the map based on the prediction of each of the models, and then we measure the travel distance. The goal is to have the minimum travel distance. First, we distribute the responders on the map strategically. Then, the first incident happens and we dispatch the closest responder to that incident. And that responder will be busy based on the travel distance and the service time. Then the second incident happens, and if the closest responder to that incident is busy and is not available, we dispatch the second closest responder to that incident. And this process continues for a whole 4-hour time window. While the allocation strategy can be separate research, the purpose of allocation here is to compare the performance of different accident prediction models. We use the well-known p-median approach to distribute the responders. For example, in this figure, the responders or ambulances are shown as green circles, and the demand nodes or roadway segments are shown as squares. And the values and the colors are representing how dangerous those segments are based on our prediction. The goal of the p-median approach is to minimize the travel distance, or these green arrows, between the supply and the demand nodes. The main caveat of p-median problem is that it does not consider the service time. Assume an incident happens here, and we dispatch this responder to this incident, and this responder will be busy during the next hour or so. And another incident happens here, but we don't have a responder to dispatch to this incident. To solve this problem, we came up with a modified p-median problem by adding another parameter to the model, which encouraging the model to put more resources closer to the dangerous segments. And it has a parameter alpha. If alpha is 0, the problem would be very similar to the p-median problem, but by increasing alpha, we are encouraging the model to allocate more resources closer to the dangerous segments. On the right, you can see the mathematical formulation for it. You're already familiar with this table, which I explained a couple of slides earlier. Now, by having alpha parameter I introduced in the previous slide, and different number of ambulances or responders, for example 10, 15, and 20, we can complete this table. Now we have total travel distance of responders per accident for 10, 15, and 20 responders, and for different values for alpha in the p-median problem. And then we have the average number of unattended accidents and the maximum number of unattended accidents for different values. You may notice that we don't have 20 for the number of the responders here, because when we have 20 trucks, we have enough resources to respond to all the incidents, and those values were 0, so we didn't mention it in this table. While the green values in each column highlighting the better performance, based on simulation, we can conclude the classical accuracy measures are not the best metrics for performance evaluation due to sparsity and class imbalance. The maximum improvement we observe is a reduction of 3 kilometers traveled by responders per accident. These figures are showing the same results from uncertainty in the prediction perspective. For example, using 15 trucks, our models show a better performance compared to the base model. Modified p-median problem improves resource allocation in general. These figures show the influence of alpha on the performance of different models with a varying number of responders. Our empirical results show that alpha values between 0.5 and 1 result in an optimal allocation of responders. Intuitively, our approach penalizes additional burden on responders. However, we also note that a large penalty can result in increased response times. This is expected as alpha grows. It discourages the geographical spread of responders. As the fleet size increases, the influence of alpha decreases. For further details, you can refer to a longer version of this paper available on arXiv. Thank you very much for your attention.